Welcome to Podcast Learn and Fun. Let's start today's journey of learning about something you might not expect to be fascinating, electron spin. Now, when I hear spin, I think of planets or maybe a basketball, but electrons aren't really spinning in the way we normally think of it, right?
Exactly. It's more like an intrinsic property, a fundamental characteristic they just have, like their electric charge. But we call it spin because it acts similar to angular momentum, like a tiny built-in compass needle that can point either up or down.
Okay, so we're not talking about a tiny electron actually rotating. It's more like this abstract spin state they can exist in.
Yeah.
But why does this even matter? I mean, they're so small. Does it make a difference?
It does. Because when you have two electrons interacting, their spins can combine in ways that affect their energy and behavior. Think about two magnets. If their poles are aligned, they repel, needing more energy to stay close. If they're opposite, they attract and settle into a lower energy state.
Ah, so those tiny magnetic fields are influencing how the electrons arrange themselves.
That's a good analogy. Now, one of the most important combinations is called a singlet state. Here, the two electron spins are paired up in opposite directions, effectively canceling each other out. This results in a total spin of 0 and is usually the lowest energy state for the system.
So it's like they've found a perfect balance, those opposing spins making them a stable, happy electron couple.
Precisely. And the stability is described by a specific mathematical equation. A bit too complex to go into right now, but the key takeaway is that it shows how those two spin states combine to create a unique low-energy configuration.
I'm trusting you on the math for now.
Yeah.
But if that's the balance situation, what happens when the spins aren't perfectly opposed?
That's where we get something called a triplet state. Here, the electron spins are more aligned, but not always perfectly parallel. Think of it like this. The total spin acts like an arrow. In a singlet state, it's 0, no arrow at all. But in a triplet, that arrow can point straight up, parallel spins, straight down, anti-parallel, or somewhere in between, giving us 3 possible orientations.
So it's not that the electrons are always spinning in the exact same direction, but there's more agreement between them than in a singlet state. And because of that, they have more energy.
Exactly. That agreement leads to a total spin of 1, and it usually means the triplet state has higher energy than the singlet state, because there's more repulsion between those tiny magnetic fields.
All right, so we've got these two fundamental ways electron spins can combine, and it affects their energy. But why should I care about what's happening on the subatomic level?
Because these seemingly abstract concepts have huge GE implications in the real world. For example, they explain why some materials are magnetic and others aren't. In materials with unpaired electrons, those spins can align and create a net magnetic moment, leading to macroscopic magnetism.
Wait, you're telling me that the way these tiny electrons are spinning determines whether something sticks to my fridge magnet?
It's a bit more complicated than that, but the interactions between those spins, whether they're in singlet or triplet configurations, play a crucial role in the material's overall magnetic behavior. And this is just the tip of the iceberg.
Okay, I'm intrigued, but my brain needs a moment to catch up. We've gone from tiny compass needles to fridge magnets in just a few minutes.
It's true, quantum phenomena often seem strange at first, but they underpin so much of our world. And it gets even more interesting when we start talking about how these singlet and triplet states influence things like light emission and even spooky action at a distance. But maybe we should save that for later.
Definitely saving that for later.
Yeah.
This is definitely one of those times where the more you learn, the more you realize how much you don't know. But that's what makes it so exciting, right?
Absolutely. And the journey of discovery is just beginning. It is amazing how these tiny spins can have such large-scale effects. And they're not just limited to magnetism. Let's talk about light, for example. Have you ever wondered how glow-in-the-dark toys work?
I just assumed it was some chemical reaction, absorbing light and then slowly releasing it. But are you telling me electron spin is involved?
It is. When a molecule absorbs light, it can boost an electron to a higher energy level. To come back down and release that energy, often as light that we see, the electron has to make a transition. Now, if the electron stays in the same spin state, like going from an excited singlet to the ground singlet, that transition happens easily and quickly. But if the transition involves a change in spin, it gets tricky.
So going from a triplet state to a singlet state is like trying to fit a square peg in a round hole. There's a mismatch.
Exactly. Those spin-forbidden transitions are much less likely. So the excited state can linger for a while before the electron finally manages to flip its spin and release its energy as light. That's why phosphorescent materials can glow for so long. Those electrons are stuck in the triplet state, slowly leaking down to the singlet state and emitting light as they go.
So glow-in-the-dark toys are literally demonstrating quantum mechanics in action. It's like a secret code. the spin state dictating how the electrons can lose their energy. But is that the only way we see this spin-forbidden effect in the real world?
Not at all. These transitions are important in all sorts of areas. From chemistry to astronomy, scientists can even use them to study the structure of molecules and how they interact with light. But perhaps the most mind-boggling application of singlet and triplet states lies in the realm of quantum entanglement.
Okay, you've officially piqued my curiosity. I've heard of entanglement, that spooky action at a distance Einstein talked about. But how do spin states fit into that?
Imagine two particles linked in a way that their fates are intertwined, even if they're miles apart. Measuring one instantly tells you the state of the other, regardless of the distance. That's entanglement. And certain types of entangled states rely on pairs of particles in either a singlet or triplet configuration.
So these spin combinations are literally the building blocks of this seemingly impossible connection.
Precisely. And this phenomenon isn't just a theoretical curiosity. It has the potential to revolutionize fields like computing and cryptography. Imagine computers that utilize entanglement for incredibly fast calculations, or unbreakable codes based on the properties of entangled particles.
It's incredible to think that these tiny electron spins, these seemingly abstract states, could be the key to unlocking such revolutionary technologies.
It really highlights how the universe operates on principles that often defy our everyday intuition. And the more we understand those principles, the more we can harness their power for incredible advancements. But as with any powerful tool, we must proceed with caution and consider the ethical implications of these developments.
Absolutely. We can't get so caught up in the potential of these technologies that we forget about the responsibility that comes with them. It's amazing what's out there when we really start to look.
I agree. There's so much more to discover, and who knows what we'll find next. This is just the beginning of our quantum journey.
Well, on that note, I think we've covered a lot of ground today. Thanks for joining us on this deep dive into the world of electron spin.
It's been a pleasure sharing this journey with you.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.